Welcome to another explainer. So today we're tackling something I know pretty much every software developer and operations engineer has felt literally deep in their bones, and that's the absolute dread of software deployment. You know the exact feeling I'm talking about, right? Your code is totally ready, the tests are green, but actually pushing it live? Man, it feels like defusing a bomb. Well, today, we're going to flip the script and transform that dread into data-driven success. Let's get right into it.
I mean, have you ever actually had to deploy way after working hours, just hoping to avoid any downtime? Or even worse, maybe you've pushed a deployment through, finally breathed a sigh of relief, only to realize an hour later that there is a critical bug, and suddenly you're frantically trying to perform a rollback while users are actively trying to use the site. It is a crazy stressful reality. But it absolutely doesn't have to be like this. We're going to look at how to escape this whole manual trap by unpacking some fantastic insights from Microsoft Learn, looking at some really cool hands-on strategies from the dev community, and digging into some hard empirical data from an IJSAT research study.
All right, Section 1, Automating with GitHub Actions.
So the very first step to escaping the whole deployment nightmare is just getting human error out of the equation entirely. We have to automate. If we look at the ideal journey of your code, it starts right at the source. When you trigger an action, say you push to your main branch, that code just flows seamlessly right into a build process. And the result? You get a clean, perfectly packaged artifact. Finally, without you even lifting a single finger, that artifact is pushed directly out to your target Azure cloud services, whether that's virtual machines or containers. It's just a beautiful, highly predictable pipeline.
But, to make that automated pipeline actually talk to Azure safely, we got to talk about authentication for a second. Microsoft highly recommends moving away from traditional basic authentication, which relies on those static publish profiles. Instead, you really want to be using OpenID Connect. Now, the absolute crucial point here is that OpenID Connect uses short-lived tokens. Yes, it's a little bit more complex to set up initially. You got to configure user-assigned identities or federated credentials, but it offers massively hardened security. You just aren't leaving these long-lasting keys lying around waiting to be compromised.
Moving on to Section 2. The blue-green strategy.
Okay, so even with a highly secure, automated pipeline, pushing an artifact directly to your live users is going to cause a little blip, right? To solve this downtime issue in Azure, we lean on a feature called deployment slots. You can kind of think of a deployment slot as this complete replica, basically a duplicate environment that acts as a live staging area right alongside your real production app. The kicker is it's hosted on the exact same infrastructure, but it remains totally hidden from your actual users.
A developer in the dev community actually provided a really fantastic analogy for this that I love. So imagine you're running a super busy restaurant, and you have two completely separate kitchens, a blue one and a green one. The blue kitchen is fully operational. It's cooking away, serving all your hungry customers right now. Meanwhile, completely behind closed doors, you are doing a full renovation on the green kitchen. You're installing new ovens, maybe testing out new recipes. That is your new code deployment. Once that green kitchen is perfectly ready and fully tested, you just seamlessly shift the restaurant's incoming orders over to the green kitchen. The customers literally don't even notice the change, and you can safely power down the blue kitchen.
So, translating that back to Azure, that shift is called the swap operation. Your automated GitHub action pipeline can actually be configured to execute the swap command for you. Once your brand new code is safely deployed to the staging slot and gets fully warmed up, the pipeline triggers the swap. Azure then instantly reroutes the network traffic from staging right over to production. Boom, zero downtime. The new feature is totally live, and your users experience absolutely zero interruption. It's like magic.
Which brings us to Section 3, the optimization framework.
So, okay, we're secure, we're fully automated, and we have zero downtime. Are we done? Actually, not even close. Because, what if that pipeline takes an entire hour to run? Exploring a really interesting study published in the International Journal on Science and Technology, or IJSAT, researchers established this optimization framework built on three core pillars: parallelism, caching, and artifacts management. And look, these aren't just fancy buzzwords. These are fundamental, structural changes to exactly how your pipeline computes, stores, and transfers data.
Let's actually break down exactly what these tactics look like in practice. First up, parallel jobs. Instead of your pipeline just running tasks sequentially, one right after another, you distribute all those heavy processing duties across multiple automated agents simultaneously. Second, we have caching. Think about it. If your code relies on these massive external dependencies that haven't even changed since your last build, why on earth would you download them again? Caching stores those intermediate results so you aren't downloading half the internet on every single build, which totally prevents that redundant, time-consuming rebuilding. And finally, artifact management. This just makes sure you're only storing what you actually need, minimizing the redundancy and seriously reducing your storage overhead.
Let's look at Section 4, Proof in the Performance.
It's always super easy to talk about theory, right? But what happens when you actually apply this framework to a real, living, breathing enterprise pipeline? Well, when researchers tracked the empirical data of pipelines before and after optimization, comparing the exact same workloads, the results were staggering. Across the board, we're talking from build times to deployment times, all the way to failure rates and resource usage, every single metric saw just a massive, massive improvement.
The most immediately noticeable win? A massive 40% reduction in build times. The average build actually dropped from a pretty sluggish 35 minutes all the way down to just 21 minutes. That is 14 whole minutes given back to your developers on every single code commit. And they achieved that simply by combining parallel execution with intelligent caching. It's a total game changer.
But as we all know, speed isn't everything. Reliability is arguably way more important. And here, the optimization framework created a 58% relative improvement in failure rates. Pre-optimization, these pipelines were failing like 12% of the time, mostly due to resource conflicts and random timeouts. Post-optimization, that dropped to a highly stable 5%. We are talking about practically eliminating those awful, highly stressful fire drill rollbacks that ruin your evening.
Oh, and there's a serious financial benefit here too. CPU and memory utilization basically plummeted after these optimizations. Because the pipelines were running so much faster and they weren't wasting time doing redundant work, the overall demand on the cloud infrastructure just naturally dropped. This directly yielded a 15% reduction in Azure infrastructure costs for the organizations in the study. So you're literally saving cold, hard cash just by making things faster and more efficient. Win-win, right?
I think the key takeaway here is really simple. The study states optimization of pipeline processes at high levels enables both faster building cycles and protection from deployment failures. Optimizing your CI/CD setup with things like GitHub Actions, blue-green deployments, and parallel caching, it isn't just about raw technical speed. It's really about delivering highly reliable, totally cost-effective business value without burning out your entire engineering team in the process.
So, we've gone all the way from the absolute dread of manual deployments to the data-driven success of highly optimized pipelines. But of course, technology literally never stops moving. The researchers in the study pointed to a super fascinating future direction, and I really want to leave you with this final thought. As machine learning algorithms keep getting better at predicting failure points and automatically allocating agents, is your current CI/CD pipeline structured well enough today to embrace AI-based optimization tomorrow? If you implement the fundamentals we discussed here, you know what? You just might be ready for it. Thanks so much for joining me for this explainer, and I will catch you in the next one.